Hello, we are in our fourth objective for the section, or our third quadric surface, and this time we'll be looking at hyperboloids. Alright, a hyperboloid is going to be in a form where all the variables are being squared. There's an x squared, there's a y squared, there's a z squared. But the signs of two of those variables are going to be different from the sign of the third one. So there's one case where two of the variables are positive and the third variable is negative. And there's a case where two of the variables are negative and the last variable is positive. And if we write this in standard form where the right hand side, the constant on the other side, is equal to a positive 1, then we can take a look at this first case and second case as a hyperboloid of one or two sheets. So our first case is in our first equation where one term is negative and the other two are positive. So think about that as one negative variable, and you have a hyperboloid of one sheet. In our second equation, that's going to be our second case, we will have two of the terms, or two of the variables, that are negative. And when we have two negative variables, then we have a hyperboloid of two sheets. Now remember that the right hand side, or the constant side, has a positive 1. That's because if the right hand side was a negative number, then we would imagine switching all the signs for the other side to make this a positive 1. And when that's the case, your signs switch and then it becomes a hyperboloid of 2 or 1 sheet instead. Alright, there's also another note here that talks about the orientation being switched if your z variable, so usually the z variable is the one that has a different sign. So in our first equation, hyperboloid of one sheet, the z is a negative and the x and y are both positive. And in the second case, we have x and y are both negative and the z is positive. And so this is oriented to open up along the z-axis. But if there was a change where the variable with the different sign from the other two are positive or negative, then your orientation is going to change. And so we'll see that in our second example. Alright, let's take a look at our first example. We have 3x squared plus y squared minus 6z squared is equal to 18. The first step is to try to get that constant to equal to 1, so let's divide everything by 18, and when we do that we're going to get x squared divided by, and 3 goes into 18 6 times, so that's x squared over 6, and then we have a y squared divided by 18, and then we have a negative z squared divided by, and then 18 goes into 6 3 times, and then now we have this whole thing equal to 1. So now it's in standard form, and this is the equation that we have. We see that we have two positive values for x and y, or two positive terms in our x and y, and our z value is negative. So we'll identify this as a hyperboloid of one sheet because there's only one negative sign. So let's label that hyperboloid of one sheet. And then how those things shape like? Well, we can take a look at traces again. If we take a look at z values being equal to constants, starting with 0, z is equal to 0, we're going to get x squared over 6 plus y squared over 18 is equal to 1. And then when we let this z equal to some other numbers, like 1, you get x squared over 6 plus y squared over 18 is equal, oops, that's a minus, so we have a minus 1 over 3 is equal to 1. Then this is still going to have a shape of an ellipse. We can bring the 1/3 over to the other side and divide by that fraction. So this is still going to be ellipse. So we would imagine up along the xy plane and everything parallel to it will have ellipses. So I'm just going to do a rough sketch of possible ellipses and how they might look like. By the way, if this was z is equal to -1, I will get x squared over 6 plus y squared over 18 minus 1/3 again, because z is going to be squared. We're going to get the same shape in the positive and negative of 1. So we think we're seeing a bunch of ellipses here. How's that relate to a hyperboloid? Well, it turns out that we'll see the hyperboloids if we let the other variables equal to constants. So if we let, for example, let y or let x equal to 1 or 0, let's start with 0. Then we have y squared over 18 minus z squared over 3 is equal to 1. So this is a hyperboloid. And if I were to draw this on the YZ plane, this would be a hyperboloid opening in the y-axis. So I'm just going to draw the rough sketch of the hyperboloid without being too technical about the intercepts and things like that. And if we take a look at the other axis when y is equal to 0, so that's essentially the xz plane, we will have x squared over 6 plus, or that's a minus, z squared over 3 is equal to 1. Again, a hyperbola in the xz plane. So I think this is opening sideways again, so it looks something like that. Alright, now let's imagine trying to draw this in 3 dimensions. So as our x, y, z space, on the xy plane we have ellipses, so we can imagine these ellipses up and down along the z-axis, ellipses that look like they're getting wider. If we draw the x is equal to 0, that's the yz plane. If we draw along the yz plane, we're opening along the y. Should be in green. There we go. And then if we draw along when y is equal to 0 along the xz plane, we're also having those hyperbolas. So ellipses and hyperbolas, you can probably imagine that this thing is going to look something like this, like a silo of some sort. And so this is your hyperboloid of one sheet. Clearly, there's one sheet that makes up the surface of the hyperboloid. So now let's do our other example, and thinking ahead, if we have a hyperboloid of one sheet that looks like a silo, a hyperboloid of 2 sheets would probably be 2 different hyperboloids, or 2 paraboloid shapes that open up into hyperboloids. Alright, let's take a look at this example. Now, as I'm looking at this example and starting off the same way we did last time, we can divide by 18. So we have x squared over 6 minus y squared over 18 minus z squared over 3 is equal to 1. now I'm noticing two negative signs and one positive sign. So we have two of the same signs that have the variables y and z, and then we have a positive sign for the x, and that has the variable x. And so that x variable with a positive sign will be the orientation, how this is going to be shaped, or how this is going to be opening up. So it's going to be opening up towards the positive and negative x-axis. And so that's one of the things that we can gather from this information. So if let's use that information to try to create how this thing might look like by looking at the traces. So the traces, remember, are the cross sections, the curves that you would get when you slice it with the plane that's parallel to the coordinate plane. And let's start with the coordinate plane, YZ plane, where x is equal to 0. So when x is equal to 0, we're going to have negative y squared over 18 minus z squared over 3 is equal to positive 1. Now this is an issue because on the left hand side we have negative quantity, and on the right hand side we have a positive 1. So this will never work for us. So there's nothing that exists on the YZ plane. Let's try x is equal to 1. We're going to get 1/6 minus y squared over 18 minus z squared over 3 is equal to 1. So we'll add 1/6 to both sides, and I'm just going to kind of scratch things out over here. I suppose we're subtracting a 1/6 to both sides. And then you got the 1/6 that we can change the signs for, the negative 1/6. I'm sorry, that's minus 1/6, so that's positive 5/6. Okay, so we're still having that issue of a negative on one side and a positive on the other. So I think maybe letting x equal to 2, maybe. I think maybe 6. I think we want this to be to match the signs. We want the values to match signs. Maybe square root of 6. So the square root of 6 quantity squared over 6 will be positive 1. And then we have the y squared over 18 minus z squared over 3 is equal to 1. So you will get negative y squared over 18 minus z squared over 3 is equal to, this is 1, we'll bring that over, it's equal to 0. So I think we have dots now. We have x, we'll have y equals 0, z is equal to 0, and x is equal to that. So I think in looking to try to graph this in 3 dimensions, our x-axis now will have a value of square root of 6 on the positive and negative side. Okay. Now if we imagine putting values that are larger than square root of 6, and it looks like it'll exist. Let's put one value that's larger than square root of 6. So anything like the square root of 9, so that's a 3. So if x is equal to 3, we will get 3 squared. So we'll get 9 over 6, and then minus y squared over 18 minus z squared over 3 is equal to 1. And then this is 3 halves, so we add that, we get 1/2 negative because it's we're subtracting that out. Is that right? Yes. And then we'll get a negative y squared over 18 minus z squared over 3 is equal to negative 1/2, and we'll change the signs to make it all positive, and then divide by 1/2, and then you'll get an ellipse. So the point is that you'll eventually get an ellipse if you go further out here in your x-axis. So you'll get ellipses that will be coming out. All right. So we're probably digging deeper than we have to in these scenarios, and really we should just look at the graphs of these things. But we have ellipses that go out that way, and then we'll quickly see that if we let y equal to 0, and if we let z is equal to 0, those are the other two variables, then we're going to get a hyperbolus. So let's do that first one. When y is equal to 0, we're going to get x squared over 6 minus z squared over 3 is equal to 1. So we'll get a hyperbola opening up along the x-axis. So xz opening up on the x-axis. And then the hyperbolus that we'll get here when z is equal to 0, we're going to get x squared over 6 minus y squared over 18 is equal to 1. And those are hyperbolas opening up along, if we look at the xy plane, opening up along the x-axis. So these are hyperbolas that are going to be opening up along the x-axis with respect to y, and opening up along the x-axis with respect to z. So it looks like it'll eventually be opening up this way and that way. Okay, so that's kind of hard to picture, so let's take a look at it using our graphing program. Here's our graphing program, and let's see, I think this is our first equation where it looks like it's something of 2 sheets, but remember to zoom out accordingly so that we're making sure that we're seeing the whole picture. So if we zoom out, we can see that hyperboloid of 1 sheet silo picture that we drew earlier. Okay, so that's our first equation, and let's take a look at our hyperboloid of 2 sheets. So here is the hyperboloid of 2 sheets opening up along the x-axis as I attempted to draw it. And if you zoom out a little bit more, you can see it a little bit clearer, and they look like paraboloids opening up on the side, but they're not actually paraboloids. They are hyperboloids. Okay. All right, so that's it for our hyperboloids. The thing to remember is that a hyperboloid can come in 2 forms. It can have 1 sheet or 2 sheets depending on the number of negative signs in our standard form. So good luck.